Okay, let's see problem 162 from the Irodov book. A small body was launched up at that angle. Find the coefficient of friction if the ascent time is 2 times less than the descent time. The initial velocity of the object, the launched velocity, is not given. And this is inclined plane problem, but we are going to attack it more like a kinematics equation kind of thing problem. So we are going to divide and conquer, divide the motion up and the motion down, calculate the accelerations, and then try to find an equation for the coefficient of friction. Okay, as I said, we are going to divide the problem as going up and going down. So this is the inclined plane. This is alpha, 15 degree, and I put over here 45. So that's not up to scale. You want to find the coefficient of friction. And they say, let's call T1 time up and T2 time down. And they say that T2 over T1 is this Greek letter, which is 2. This is 2. Okay, when the block is going up, is launched, we don't know the initial velocity. And if we do the free body diagram, you have mg, the normal force, and friction is in this direction. And we are going to make this direction positive. So this is alpha is the angle between two perpendicular lines, so this alpha is equal to this alpha. And then mass times acceleration, let's call acceleration up, and A2 acceleration down, is negative F, the friction, and this component over here that is opposite to alpha, so it's mg sine of alpha. This is in the x-axis. In this axis over here, y-axis, we have that n is positive, and this component over here, which is mg cosine of alpha. And the object is not going flying up or sinking into the plane, so this is 0. So the normal force is mg cosine of alpha. So the friction is mu times n, so it's mu mg cosine of alpha. That means, putting the friction back on this equation, we have mu mg cosine of alpha, it's a negative, minus mg sine of alpha equals m times a1. As you see, the mass cancel, and a1 is, and taking g as a common factor, mu cosine of alpha plus sine of alpha. And now we could get the kinematics equation since we already have the acceleration. So we have the kinematics equation from the position. So let's say it goes from 0, cover that distance L, that is not given. So you know that L is going to be v naught, that is not given, that's the launch velocity, times t1 minus, because the acceleration is negative, 1/2 g mu cosine plus sine times t1 squared. So that's one equation. The second kinematic equation is the final velocity. Do you know it's 0 at the top? Is the initial velocity minus g minus, this is, guys, this is the acceleration, and the same over here, mu cosine of alpha plus sine of alpha t1, and we know this is 0, and we have an equation for the launch velocity, g mu cosine of alpha plus sine of alpha times t1. Okay, so we have two equations here. Let's call this 1 and 2. But I had to introduce variables, and I introduce L, that is not given, and introduce v naught, that is not given. And now let's analyze the situation when the block is going down. It's reached the top position, so now the initial velocity is 0, and it's moving at some velocity over here, and this distance is L. Again, you have to be consistent between this problem and this problem, so I'm going to keep this direction as being positive. And the free body diagram is similar, but now because the object is going down, the friction is opposite to the motion in this direction. And again, this angle over here is alpha. So in the x-axis, I have positive friction, and this component over here of mg, that is opposite to the angle, so it's sine a2. a2 is the acceleration downward. And similarly as in the previous one, the normal force is equal to mg cosine of alpha. I'm not going to do it, so this is mu mg cosine of alpha minus mg. Now the mass cancel, this cancel, and a2 is g times mu cosine of alpha minus sine of alpha. And again, I now use the kinematic equation. L, this displacement, this distance L, is the initial velocity that now is 0. minus the acceleration. How we put plus acceleration? Over here was minus because this minus over here. 1/2 the acceleration A2 times, and this is T2 squared, and the acceleration is that. So I have an equation for L. So now I have three equations, and the unknowns are L, mu, and B naught. But I have three equations, so I can stop here and try to solve it using these three equations. So equation 1, equation 2, and equation 3. Okay, so 1 is equal to 3. So I get this equation. And I'm going to substitute B naught into here. We put this in here. And T1 times T1 is T1 squared. As you can see, these terms are identical. And I forgot to put the square over here. These terms are identical, so 1 minus 1/2 is 1/2. Now the 1/2 G cancel, and I will divide by T1 squared. And the reason I'm doing that, because this is what is given. This is 2, and it is T2 over T1. So I get mu cosine of alpha plus sine of alpha. The T1 cancel. And on the other side, I have mu, parenthesis, cosine of alpha minus sine of alpha times mu squared. I'm going to divide by cosine. I'm going to divide by cosine. So I end up with tangent, tangent, tangent. So I got mu plus tangent mu and I'm going to multiply now. Minus tangent mu square. So I'm going to move this to this side, so it's negative, and I'm going to move tangent of alpha this to the other side, and it's positive, so I end up with tangent plus tangent times mu squared, and here mu square, and this is minus mu. Now over here I take tangent as a common factor, and over here I take mu as a common factor, and let's continue over here. I think I have space now, so the coefficient of friction is 1 plus mu squared minus 1 tangent. Let me rearrange it. I think they have it in the answers like this. And you know what alpha is? Mu squared is 2. So let's check. So it's 5 over 3 tangent of 15. I look up the answer and this is wrong. The answer is supposed to be 1.16 for the coefficient of friction. And let's see, kind of find where the mistake is. Again, here the displacement is from 0 to L. So the final is L and the initial position is 0. So it's L minus 0, which is and this negative over here is because I have it here, so I put it here just to be consistent. But over here I have the axis in this direction, okay? So it's going from here to here, so the displacement is negative L. That means that this equation is, and I will swap the sine and cosine over here. So this is equation 3, which is the same as putting a minus over here. Putting a minus over here, that's what the mistake was. I mean, there is a minus over here. There is a minus over here. There is a minus over here, and here I will put plus. And, okay, I mean negative. Let me see, step 1 was wrong. So it's mu plus tangent of alpha. That's the left hand side that has not an issue. But here if I put a minus, it's going to be minus mu plus tangent of alpha and multiply by mu squared. Then I move this to this side and this to this side, so I get mu plus mu squared, and here tangent of alpha minus tangent of alpha plus tangent of alpha mu squared. So mu is mu squared plus 1, common factor tangent, and mu squared minus 1 minus tangent and positive vector. So mu is mu squared minus 1, I mean that Greek letter, plus 1 tangent of alpha. And this is the correct answer. I checked. So mu is 4 minus 1, 3 over 5 tangent of 15, that is 0.16. So remember that this kinematic equation that was used, if you have to be careful which one is your final and your initial. So when it's going up, is from 0 to L. Initial is 0, final is L. But when it's going down, initial is L and final is 0. So if you add x minus x naught, is when it's going up is plus L, and when it's going down is negative L. And you always put these numbers positive. Just be consistent with the direction of motion. You keep this as positive. And if the accelerations come out to be negative, you could just put this negative because this is negative. And in that way, you are less prone to make mistakes like I did.